So this is HPAB board. It is responsible for the obviously HPAB bus communications, and it is completely built on this specialized Texas Instrument chip MP9914NL. Also it has some bus transceivers here and there and some logic, and that's it. This is A7, a digital control board assembly. So as you can see, it has very interesting dual CPU design actually. So this chip is actually a microcontroller which has its own RAM, ROM and I/O port controls. So this is 8-bit Fujitsu microcontroller named MB654810U, and it's probably used for the analog board control operations like ranging, balancing, relay switching and other stuff. While this one, a Motorola MC68HC30FN8, this is a 32-bit CPU, and it is responsible for the operation system and menu, storing and reading various data and so on. Also here we can see this IC. This is analog interval timer, and its name is IS82C54. So on the right side we can see 6 EEPROM ICs, and these ones are AM27C512, some RAM chips, not much, and these are the EEPROM. So these are electrically erasable rooms, and this is where device stores its calibration data, short and open calibration, and some measurements if you actually enter in the values in the table. Here on the left we have LEDs which show the initialization state of the board, and here is how the board looks on the other side. More than 2 layers board. I do not know how much it has, but as you can see, this side is completely covered in shielding. No traces here, as well as here. No traces visible. Everything is covered with a shield. They really did care about the shielding. Also at the bottom we have some bus buffers and logic as well. So the model name for these RAM chips is the TC5525-7DPL85L. As for the EEPROMs, we have HN58V66AP10. So this is a 5 signal source board. This is where the signals gets prepared and fed into your device under the test, or into the high power amplifier or bias A4 board, if you have that option installed. So let's start from the right side and move to the left. This is how the signal preparation is working. So this cable, it feeds the clock into this part of the digital circuitry. So the main signal is created from these 3 crystal oscillators. They are connected depending on the frequency you have selected: 19.2 MHz, 16 MHz, and 15.36 MHz. So each of them can be connected to the next stages, and then we have this board. Let me show it better. So this board contains different flip-flop counters and various logic. This part of circuit works like a divider. It divides the frequency from these crystal oscillators, and then the signal goes into this part of the circuit, which creates a quasi-sine signal based on this frequency that we obtained after the division. So the quasi-sine signal then is fed to these two decks, which are ID 9708AR. We have two of them because this circuit generates two quasi-sine signals. Each of them has a phase difference of 90 degrees. The quasi-sine signal then enters the reference signal of the deck, and then based on that the decks generate the sine wave. So one of the signals has a 0 degree shift in the phase, and other signal has 90 degrees. Next, the signal goes through some kind of amplification, but it looks like they are part of the low-pass filtering circuitry. So next we have whole this section is actually a low-pass filters. Because the schematic is not available, I assume that all this circuitry here is responsible for strict or static low-pass filter, and these two boards are configurable low-pass filters. So the variable low-pass filters are actually configurable from 200 Hz to 100 kHz, and other two are actually working in frequency ranges from 100 kHz to 300 kHz and from 300 kHz to 1 MHz. These configurable low-pass filter boards are identical. They contain a lot of precise resistors, op-amps, comparators, which all are the part of this circuitry. So the 90-degree shifted signal goes through its own configurable low-pass filter and then it goes to the different part of the device. It's not used as a main signal source. And next, after coming out of the low-pass filter, the main test signal is actually switched by this analog switch. So it connects here, here, and here, and then depending on the frequency settings, the signal goes from the output. Also here we can see some caps, inductors, and linear voltage regulators, which are used as power supply, as a dedicated power supply to this board. And we have some digital logic to control all the switches and some digital circuitry. Next in line, they have another one, analog to digital converter. This is AD7524. So while these ones are actually voltage output DACs, this one is actually current output, and this one is much more stable. So what they are doing, they are controlling the output signal with the help of these DACs to a certain degree as well. And this one is just used to stabilize the output sine wave to make it more precise. The next step for the signal is to get some attenuation, and here we can see these two boards. These are configurable attenuators. So we have a lot of resistors here, and according to the numbers, they are really precise. So these two analog switches are controlling and switching the resistors here on these small boards. Next, the signals is coming out of the attenuators and go through the final amplifier, which is here. These are these two transistors. These ones serve as final output amplifier with a gain 1, with a gain 2. And then we have some protection diodes, and it goes out of this connector. Also, we have this small circuitry here, which serves as DC bias, so it can generate 1.5 volt and 2 volts, and then these voltages are just connected to the main output using this analog switch. So this is how the board looks underneath. But at the top side, almost everything is covered by this complete copper screen. So the board that I'm showing is recently new. It was made in 2002, but the original device was created by the HP in the 80s. So as you can see, at that time they took a lot of efforts to make this signal generator configurable by the frequency, by the voltage. They use so many transformations here to precisely control the output voltage and the frequency of the test signal. So I checked the PCB once more, and I confirmed that all these traces are just digital logic control signals and power lines. This is A4 high power DC bias optional board, and it allows the device to go up to 20 volts and 200 milliamp of the measuring signal power. So the signal from the A5 signal source board goes into this connector through this relay, and there's additional times 10 attenuation circuit. I can see Dale high precision resistor here, probably just switched by a single transistor, and then it goes directly to this high power amplifier. The amplifier coefficient is 10, and it is strictly defined and it's not configurable. And we have output resistor here, and the signal from this resistor goes directly to the output. So also there is an additional heatsink at the back shielding, which is connected here, and it's cooling down the resistors. Also, there is a dedicated power supply. For this amplifier, it is switching type power supply. There is a dedicated controller IC for this, which is UPC 484C switching transistors and transformers. It probably creates like something plus minus 30 volts for this amplifier. Again, some linear regulators for the dedicated power supplies as well. Here and here, these ones are supplying probably the amplifiers, the operational amplifiers here, and the output stage is fed by this power supply. Also, there is a separated DC bias function here, and it consists of DAC, and the DAC name is, the DAC model is AD7540N41, and the reference is based on the LT1021. As you can see here, it's nice 5 ppm reference voltage, and it works in 5 volts mode. There's a op-amp AD711JN that acts as a buffer for this reference, and this looks like a metal foil divider here. I cannot read the model, but here it is. probably it adds like feedback resistors to set the exact output voltage. So this is circuitry. It just controls the DAC values, and additionally, after we have the reference and the DAC working, the output voltage is get buffered but by the op-amp, and then we have additional attenuation circuit which allows the device to set this reference voltage to desired value, and the attenuation is done again by the op-amp and this analog switch IC, which is MC14052B, and we can see these precise resistors here, which are actually switched as voltage dividers for the reference signal, or they might be just be located in the op-amp feedback network. So this is more correctly to do so. Anyway, so once we have input signal, it can be mixed by this relay together with the already amplified signal, or it can be connected directly to the input signal. So as you can see, it's very simple board, despite it's too big and heavy. Nothing special. He'll just reference DAC divider attenuator here, and additional attenuator for the input signal, simple 10 times amplifier, and which goes the power supply for this, and then the signal is the already amplified signal goes through this connector. Also we have output to the bias monitor. So this is not we are not measuring the signal level, just for the DC bias. So this is how the board looks at the bottom. So far it looks like just a simple 2-layer board, nothing special. So this is A3 range resistor board. So the high potential goes into this connector, and we have 3 main things on this block. So generally this purpose of these blocks is to amplify high potential signal from the device under the test, but I actually do not see any amplifier here. This LM393N is actually a comparator, so probably that amplification is done with these resistors. And as you can see, we have 2 Vishay precise metal foil resistors on this side, and they are used to switch between 1 and 10 gain, and that's all it does. There is just a switch for the application for the 10 times, and the switch is done with this relay. Unfortunately, the resistors are soldered facing to each other, so I cannot read them, and I will not touch them to not change any resistance values from the mechanical stress. But this is definitely an amplifier, because we have a low pass filter board here, and it's similar to the ones that are located in the other boards. So this board looks like this, and we have another low pass filter here and another one here. This block contains range resistors, modules, and switches. Low current signal goes into this connector, and then we have the op-amp, which is TL071CP. That's the main op-amp here, and in its feedback circuitry are connected these boards. These are sets of resistors, and analog switches. So they use this 74HC4053 multiplexer to switch range resistors, which are located on these three boards. They use SMD precise resistor there. I cannot read their exact values because they are soldered quite close to each other. So also we have another three Vichy foil resistors here. This AC is just a relay driver. So I assume they use relays to switch this resistor because they are extra precise and stable. Except the range resistor, there is the current amplifier, and I assume it is created with these discrete components, the resistors, because this stage looks like the output stage of the symmetrical amplifier, and these are just main load resistors here. And this block has an active inductor circuitry and current to voltage converters, and it's really hard to tell what is where, but we have this two LM324N quad op-amps with custom Agilent specific resistors arrays, and these are 100 ppms. So I assume they are used as a separate current to voltage converters, and each of the M plus resistors is creating a separate range switch. Also we have this high frequency LF411AC amp and some other circuitry is probably used for the actual active inductor, because we have capacitors here near the resistors, and usually the active inductor is just a resistor and the capacitors in the feedback of the op-amp connected. And the low potential signal from the device in the test goes into this connector and is output from this connector. Also you can see the shielding, it's pretty good. But the main analog connectors are on the back side. So it's double layer board as it looks like. No additional layers are visible. So this is A6 phase detector and ADC board. So the high potential and low current are coming in through these connectors. And first stage is a current source. And looks like this current source is built based on the transistors. Then we have a configurable capacitor, and it consists of basically this analog switch HC4052 and capacitors. These are discrete capacitors that are connected through the switch to the main signal in series. Another analog switch used as a programmable attenuator, because the schematic says there is two attenuators on this path. Then we have amplification stage, and then another analog switch with a resistor in its network, and then we have a phase detection circuit. So when the signals are actually reaching 80 degrees phase, the signals gets measured by the ADC. I assume that phase detector is built based on this board. This is how it looks like. This ceramic board are actually identical. And we have 600 megahertz HA12539 amplifier, and I assume these amplifiers are the same. They are having the same ceramic package as this one, but additionally they have heat sinks installed. Output amplifier is LT1007, and then the signal is reaching the ADC. The logic here is actually just creating timings and measure and controls the ADC circuit as well as these analog switches. So here's how the ADC converter looks like. As you can see, it has some traces of electromechanical low voltage design. It has these PTFE standoffs. So this is A2 modulator board. So the signal comes through this connector, and first block that it makes is the oscillation level normalizer. So this section is full of analog switches. These are HC4050N and two high-frequency operation amplifier. And we have a lot of capacitors and resistors, which are obviously are working as like configurable capacitors or like variable capacitors, and some of these resistors are used in this op-amp feedback circuit to change the attenuation level or the amplification level, and the logic to control all the switches is located here. So again, we have three analog switches, two 400 MHz operation amplifiers, and then the signal goes into this section. So it has these two boards, and this IC is MC1496 and this one is 1496 as well, but in the different package. So both of them are modulators, the modulator with the ability to control the gain. So I guess this is where device is doing some signal modulation. And this is just a quad op-amp, and it's TL074C. On this side we have oscillation level normalizer 2, which is very similar to this one. It has the same analog switches here, some op-amps, and 600 MHz of operation amplifier, and the same model as here and in the previous board, and additional modulation, the modulator board here. So this, what it's doing is just switching it also has the variable capacitors, which are just connecting through these analog switches when they are needed. And also these amplifiers, and these are probably also switching their feedback network resistors to change the gain. And another analog switch here with the capacitors that are connected to it, so it acts as variable capacitor as well. So this is the complete board, and you can see it has a lot of guard traces here. Here are they, a lot of them, and this is mostly in the modulation section. So this is A1 power supply board. And let's talk about the elements that are located here. So this transformer, it's a regular transformer. It doesn't participate in any switching actions. It is here to feed, to kind of lower the voltage and feed the switching control circuit, which is located here. And that's its only purpose. So the mains line gets reduced by this transformer, then it gets rectified by this rectifier. And we have linear stabilizer here, and it feeds this IC. And this IC actually the switching control and the voltage control and everything. It does everything in this switching power supply. So the IC model is the same as in other boards, and it's a UPC 494C. These are the main switching MOSFETs, and the models are 2SK386, and they are both identical. The schematic is available for this board, so you can investigate it by yourself, but I will just show the main elements here. So this transformer is just an isolator for the gates for these MOSFETs. That's another attempt to make the power supply fully isolated from the mains, so not any switching noise or spikes will get into transistors, and then it may get into the primary winding of the main switching transformer. Then we have the input fuse, and then we have this small refa capacitor here. And these ones are good ones. I met them many times in a different HP devices, and I have much older ones, and they're all fine. There are no cracks. That's because they are small. And the larger ones, they actually will fail in 100% of cases. You need to replace them, but not these smaller ones. So there are two of these, and they seems to be pretty fine, pretty good. Okay, then the voltage goes through here, and this is the resistor that acts as a current limiter, and it gets shorted by this relay. So once we have the voltage in the output, it gets stabilized and lowered by this linear regulator, and it feeds the actual coil of this relay. So once the output voltage has appeared, this resistor is short and the power supply goes into full current. That's just a safety action. So if you have something wrong here, the whole power supply will be not overloaded by this problem, because there's a current limited resistor here. So this is some mains filtering here, capacitors, and the voltage from the main gets switched by these MOSFETs. The main pulses are going to this primary winding here. So as you can see, the primary winding made from the shielded wire. It has a PTFE insulation, and it's just two windings here. Just two windings. That's because they are trying to attempt to isolate as much as possible the common mode noise and different type of noise of the secondary part of the power supply from the mains. Also, this is actually, I forgot to mention that this is a mains transformer. Actually, it's the one that does the transformation from the main output voltages. It has two shieldings. One is actually shielding the primary winding, and second shield is shielding the secondary winding, and those shields have different grounds, so that that shield is reduce the capacitance of this transformer, reducing the noise ingress and the common mode noise ingress from the mains even further. So this makes the design really silent. There's another winding here. This is a feedback winding, and goes to this inductor. It's not a transformer, just a filter inductor from the feedback winding. And this goes into this control IC. As you can see, actually there is no control of the output voltage on the secondary windings. There are 3 optocouplers. One just sends the power phase signal to the other parts of the device, and these two, one of them is controlling the presence of the output voltages, and second one is controlling the fan. So this power supplies creates very many voltages, like plus minus 5, plus minus 12, plus minus 15, plus 21, plus minus 48. And if one of those fails, there is a signal that is sent through this optocoupler to this controller IC, and it shuts down the power supply. And the same happens with the fan. The fan has 3 wires coming from it. One of them carries the voltage that shows that the fan is spinning, and once that voltage is gone, through this optocoupler, the main switching IC will shut down the power supply. Then we have the secondary windings coming from these here. This is another common mode filter for the secondary winding this time. All of the secondaries except 5 volts are going through this inductor filter, except the 5 plus 5 volt rail, and it has its own inductor here. On the final stage we have these bridge rectifiers. They all for the 5 volts, plus minus 12, plus minus 15, and that's basically everything that we have here. So the secondary voltages, they are not stabilized, completely not stabilized. The only feedback that we have is through this primary winding. So that is why each board in this device had its own linear regulator, because these voltages are not controlled in any way here. So as you can see, this is a pretty complex board, but the main goal of this was just to reduce the connection between primary and secondary as much as possible, as I think the main problem was the low frequency common mode noise, and that's why I created such a complicated transformer here, and they even galvanically isolated the gates of the transistor from the switching control IC. And this is how the board looks the back side, and this is a really simple 2-layer board. And it has the shielding for the top and for the bottom.